Hello. This lecture is on section 2.3 from course Math 311, a course on linear algebra at Western Illinois University. The topic today is spanning sets and linear independence. So last time we learned how to solve linear equations using Gaussian, or systems of linear equations using Gaussian elimination, which involved some elementary row operations. And we're going to use there are some very interesting consequences of that method, because it leads us to talk about some more general concepts, that is linear independence and spanning, and spans of vectors. So I think the most important thing you can get from this lecture is right here at the beginning, is that any system of linear equations actually corresponds to a linear combination of vectors, because here we have m equations and n unknowns, and assuming this has a solution, that means there are real numbers x1, x2 through xn, such that this is true, right? Because remember how we add equality of vector, what this just means is x1 times a11 plus x2 times a12 plus xn a1n is equal to b1, and that's basically this first equation. So every component here from this vector equation corresponds to a linear equation here. So a solution here corresponds to a linear combination here, and in fact these are just column vectors, and we can call this one a1 and this one an, and we can call this one b. So the eighth I actually will just be, if we look at the corresponding augmented matrix of this system, the AI is just the ith column of this coefficient matrix A. Okay, so this holds if and only if this holds, if and only if this holds, and we said that again, this is the same thing as saying that B is a linear combination of these columns. And another way of saying this is that B is in the span of these columns. So we just want to define the idea of a span. A span just means the span of some vector, a set of vectors, is just the set of all linear combinations of those vectors. So if v1 through vm are vectors in Rn, then the set of all linear combinations of those vectors is called the span of those vectors. In other words, the span of v1 through vm is all vectors of this form where the c's are real numbers. And if in some cases the span of a set of vectors will be all of Rn, then we say that this set is called a spanning set for R1. So for example, 1, 0, and 0, 1 is a spanning set for R2. Okay, but the spanning set is not unique. We found out previously that the vectors 1, 1, and 1, negative 1 would also be a spanning set for R2. Obviously, the vectors 1, 0, 0, 0, 1, 0, 0, 0, 1 would be a spanning set for R3. Okay. Later on, we'll talk about that this one and this one is actually a special name for that. It's called the standard basis, but we're not quite there yet. Okay, so question is how. So we'd like to be able to know how given a which vectors are in the spans of certain sets. Okay. So that brings us to the next example. Suppose we wanted to find out if 1, 1, 2, 4 is in the span of these vectors 1, 0, 1 and 1, negative 1, 2. Obviously, we're working in R3. Okay. So in other words, what we want to do is we want to find numbers x1, x2, x3, such that x1 times 1, 0, 1 plus x2 times 1, negative 1, 2 is equal to the vector 1, 2, 4. Okay. All right. This will correspond to these three equations. We have 1 times x1 plus 1 times x2 is equal to 1. So we get that x1 plus x2 equals 1. We get 0 times x1 minus 1x2 is equal to 2. So this is minus x2 equals 2. And then we have 1 times x1 plus 2 times x2 is equal to 4. So we get x1 plus 2x2 is equal to 4. Okay? And this system is relatively easy to solve, right? We can, so this, the second equation automatically gives us that x2 has to be negative 2. And x1 is going to be, then what does x1 have to be? Well, x1 is going to be 1 minus x2, which we just found is negative 2. So x1 is equal to 3. But it's going to turn out that this does not work, because we can't forget about this other equation says that x1 is going to be 4 minus 2 times negative 2, and this is 8. Okay, so we can't have x1 be equal to 3 and 8 at the same time, right? 3 is not equal to 8. So there's no solution to this system. But the question is, what is this in the span? And we just said the answer is no, because there's no real numbers x1 and x2 for which this is true, right? So the answer is no. Now we could also, this was relatively easy to find, but we could also, if we wanted to use Gaussian elimination, we would say that this system actually corresponds to the augmented matrix 1, 1, 1, 0, negative 1, 2, and 1, 1, 2, 4. Okay, and using elementary row operations, we can see that it's actually not too hard to put this in reduced row echelon form. This way we can add, there's already a 1 here, a 0 here. We can multiply the first row by negative 1 and add it to the third row, and we get 1, 1, 1, 0, negative 1, 2, and then we get 0, 1, 3. Okay, and we can add the second row to the first and the second row to the third, and we'll get we do two operations at once, and we get 1, 0, 3. Let's see if we do, is that what happens? Yeah, yes, it does. Let's see, it's, okay, oh, I see what I did. We'll just do this step by step. So this is 1, 1, 1. And we'll start out by changing this sign of everything in the second row. Okay. And then we can add, now that we have a 1, we can multiply this row by negative 1 and add to this row, and we'll get 1, 0, 3. Okay, looks like we still get the 3 here. And then we get 0. We add negative 1 plus 1 is 0, and negative 2. So this would be 5. And as soon as we get down here, we don't even have to really do anything else. As soon as we get down here, we get that 0 is equal to 5. All right, because so that's a contradiction, right? So again, we get no solution, right? All right. Yeah. Although I will say that if we kept doing this, we would get the reduced row echelon form of this matrix would be this. Okay. So once again, we get no solution because 0 is not equal to 1. All right. If we look at example 2, let's say, okay, well, is this vector in the span of these two vectors? So we'll keep the two vectors here. And if we do that, well, we can just basically this, because these vectors are the same. This equation is going to be the same thing up here, except we're just replacing 1, 2, 4 with negative 4, 7, 3, negative 11. So we get x1 plus x2 is equal to negative 4 minus x2 equals 7, and x1 plus 2x2 equals negative 11. And if we solve this, we automatically get x2 has to be -7, and then x1 is -4 minus x2, which is -7, so that's -4 plus 7, that's 3. And now we'll check and see what happens here with x1. x1 will be -11 minus 2 times -7, and that's minus 11 plus 14, so that's 3. So this time these two agree, all right, and that's good. So we get that. X1 is 3 and x2 is -7, and in fact we get that 3 times 101 plus -7 times 1 -12 is equal to -4 7 -11. Okay, so this is a linear combination, and our answer is yes. Okay. We could have also, and by the way, we could have also done the same thing with solve the system doing this way with Gaussian elimination if we wanted to. All right. I should say that these actually are not unique. There might be other. Well, I won't say whether they're unique or not just yet. Okay. I think we can see that these all have to be unique because we found that there was just a unique solution here. Okay, so that's what I meant to say. All right, to stick with these examples, just want to say, we can learn a few things here. Because we just proved that this vector is a linear combination of these two vectors. So this vector is clearly in this span, okay? And I think you can see that as a result, any linear combination of these three vectors will also be a linear combination of these two vectors, right? Because if this, let's say if this is V1 and this is V2 and this is V3, okay, then any linear combination of V1, any linear combination of these okay, well, we can write this is going to be C1 V1 plus C2 V2 plus, and we just found that V3 is in fact, what do we say it was, 3V1 minus 7 V2. Okay, so we can collect like terms and we'll get this is C1 minus 3C3 V1 plus C2 minus 7 C3 V2, right? So any linear combination of these three vectors is actually a linear combination of these first two vectors, okay? So this is contained in here, and of course any linear combination of these two vectors is also in here, right? So because this the third scalar here can just be 0, right? So these are equal, and in fact what's the geometric application of this? Well, here we're talking about any linear combination of this. So if we have like xy, if we say that xyz is in the span of these two vectors, we're talking about that xyz is some number, well, I guess we can call it C1 times 101 plus C2 times 1 -12. And this tells us that x1 is some number times this vector plus some number times this vector. We can use C1 and C2, or we can use R and S if we wanted to. We can call these anything we want. And this actually is the vector form for a plane. Okay, and in fact, the span is the plane given by x minus y minus z equals 0. Okay. And in fact, this is not just a plane; it's a plane through the origin. So there's no constant vector here. Why was it one? You can check that. In fact, you plug 1, 0, 1 in here, you get 0. You plug 1, negative 1, 2 in here, you get 0. Okay, so this is these two vectors are orthogonal to the normal vector of this plane. So the span is the plane. Okay. Now, in general, as long as if you take the span of any two vectors, as long as they're not multiples of each other, the span of two vectors is going to be a plane in R3. All right, and there's a reason for that. We'll come back to that very shortly. In this example 4, if we go going back to this really example 1, when we showed that 1, 2, 4 is not in the span, so this is because 1, 2, 4 is not in here. There's no, and 1, 2, 4 is in here. These spans are not equal. Okay, we just showed that this is a plane. We showed that this is a two-dimensional plane. This is a plane in R3, and here we have a span that we basically have we added another dimension. Well, R3, we haven't defined dimension yet, but we kind of know that R3 is space. And, there's really nothing really between a plane and three-dimensional space, in terms of spanning set, the span of vectors. So it turns out that this is actually going to be R3. Now, if you want to see why, remember, any vector in R3 can be written as ABC. And it turns out these can be written as a linear combination of these three vectors. So now, where do these ugly fractions come from? Okay, how am I just a genius? No, I'm not a genius. I just know how to compute. We know how to compute do Gaussian elimination now. This is where this comes from, and in the next page I've sort of outlined where this came from. Really, we just wanted to find three numbers such that three numbers like x, y, and z, such as x times this vector plus y times this vector plus z times this vector is equal to the vector ABC. So basically, we want to solve this system of linear equations, and we do that by Gaussian elimination. Okay, you can follow this, and we were just doing the only difference here, instead of 0, 0, 0, we have A, B, and C. We're just treating these as unknowns or constants, and so we just basically we can use the same elementary row operations we did before. We can add R minus R1 to R3. And then here, what we did was before we changed the sign of this entry, we added this row, the middle row, to both the top and the bottom. That's how we get these zeros. And then we changed the sign here, and then we divided this last row by 5. And then we just had to do for the last one, we wanted to clear out these two entries, so we added 2 times this row to this row, and then negative 3 times this row to this row, and then we just do a little bit of algebra here and simplify, and we get this. Okay, so that's where these go. So in this case, this is our solution for x, y, and z, and so that's why we get this times the first vector plus this times the second vector plus this times the last vector is equal to a vector ABC. So that's where we got this. Now, where we get this. Now you say, oh my God, are we going to have to do this on a test? Well, not necessarily. Well, I want you to see where this comes from, because what we've actually done without knowing it is we have actually sort of computed the inverse of a matrix, but we haven't talked about what inverses of matrices are. But yes, we will. But we will come back to this. You don't. I don't think I'm going to have to ask. I don't think we're going to have to do this on the homework. But you know now where this stuff comes from. Okay, because you will actually need to know how to find spanning sets. So this always works if you're trying to determine if something is a spanning set. for Rn. Okay, so getting back to the example here, something very, so we can see that here we have, in both cases, we had a span of, here we had 3 vectors, and the span of these 3 vectors was two-dimensional, whereas the span of these 3 vectors was 3-dimensional. And we have a special term to describe what's going on, because these vectors are we're going to say that these are linearly independent, and these vectors are dependent. And they're dependent in the sense that this vector is dependent or can be written as a linear combination of these. Okay, so we get into a very important definition of linear independence on the next page here, and we say that a set of vectors v1 through vm in Rn is linearly dependent if there's some linear combination of them equal to 0 for some real numbers c1 through cm, not all 0. And this is important, because obviously if you let all the c's be 0, then of course this is always going to be true. Okay, so we want some non-trivial linear combination of them equal to 0. Some of these could be 0, but at least one of them is not 0. Okay, and so that's what linear dependent means. And we say a set of vectors is, if it's not linearly independent, if it's not linearly dependent, then it's called linearly independent. Okay. Well, that means there's the only solution to this would be if these vectors are linearly independent, then the only c's that work are when they're all 0. It's important to note that when we talk about independence, linear independence or linear dependence, we're talking about sets of vectors. In general, it's not going to make a whole lot to say, oh, this vector is linearly independent and this vector is not. We're talking about collections of vectors. Because if you just talk about a set, a one-element set, that's always going to be linearly independent unless this is the 0 vector. Okay. If you have a pair of vectors, and let's say they're non-zero, then they're linearly independent if and only if one is not a scalar multiple of the other. Okay, right? Because if v1 is equal to lambda v2, then we can always write 1 times v1 plus negative lambda v2 is equal to 0, right? Okay, so the linear independence, when we're just talking about 2 vectors, in linear independence or linear dependence is easy to find. You just see if they're scalar multiples of each other. Another thing, important fact, is that if these vectors if a set of vectors is linearly dependent, but that happens if and only if at least one vector can be expressed as a linear combination of the others. Right? We saw as soon as that happens, then we get linear dependence, and the reason for that is as follows. Okay, let's say v1. Let's say v1 is a linear combination of all the others. So let's say we have v1 is equal to c2 v2 plus cm vm. Okay, and then v1 is not 0. Let's say we're assuming that v1 is not 0. Okay, I guess we'll just make it. We'll say it's not 0 to be simple. But then we can basically subtract v1 from both sides, and we'll get 0 is going to be negative 1 v1 plus c2 v2 plus cm vm. Okay, and so here, obviously negative 1 is a non-zero scalar, so 0 is a non-trivial linear combination of these. So that means we get linear dependence. Okay. It's not. It says at least here. It might be that not every vector here is going to be a linear combination of the others. Okay, but at least one of them has to be. Another fact is that what follows from this, and what we've talked about, is that if if V1 through Vm are column vectors in Rn, and A is the matrix formed, whose columns are just these vectors, then this is linearly dependent if and only if the homogeneous linear system with augmented matrix A0 has a non-trivial solution. Okay, and that goes back to what we talked about at the beginning. Goes back to this. This is a special case where this vector is just 0. Okay, so if this is 0 and one of these x's is non-zero, then these columns are these column vectors are linearly dependent. Okay, otherwise they're linearly independent. Okay, and we said last time is that with homogeneous linear systems, you just have to look at the rank of this coefficient matrix A to see if we have, because we're either going to get a unique solution, that is the trivial solution, or we're going to get infinitely many. Okay, and remember, rank is of course the number of non-zero rows in the matrices reduced row echelon form. So we had from the rank theorem last time, we get that if the rank of A is less than m, then we get a free variable, and that means we get infinitely many solutions, and so we get a non-trivial solution, and then that's how we get linear dependence. Okay, so let's just close with a few examples. Okay. In this example number 5, is 1, 3, 5, 15 linearly independent? Well, I think you can clearly see that this is 5 times this vector, right? So they're scalar multiples. So we can automatically say that the answer is no, they're linearly dependent, because we can write 5 times 1, 3 plus negative 1 times 5, 15 equals 0, 0. Okay, so actually they're linearly dependent, and a lot of times in the homework they'll ask if vectors are dependent, they want a dependence relation. So that's what this is. All right, so that was pretty easy. Now things are not quite as easy in R4. Here we're given that here we have 3 vectors in R4, and we want to know, are they linearly independent or not. So here what we do is once again we want to write, reduce this to a system of equations. We'd say, okay, can we find an x1 times this plus x2 times this plus x3 times this equals 0, and that's going to correspond to the system, and that system corresponds to the augmented matrix. So we can actually just go directly to this and say, let's say we have 1, 1, 3, 0, 0, 1, negative 1, 0, negative 1, 1, 1, 0, and 1, 2, 1, 0. Okay. Okay. So we do our elementary row operations, and fortunately we already have a 1 up here, we have a 0 here, we want to make these two 0, so we'll multiply this top row by we'll just take this row and add it to the third row, and so we got 1, 1, 3, 0, 0, 1, negative 1, 0, 1 plus negative 1 is 0, 1 plus 1 is 2, 3 plus 1 is 4, and 0 plus 0 is 0. And then in this case we want to get rid of this 1, so we'll multiply this row by negative 1 and add to this one. So negative 1 plus 1 is 0. Negative 1 plus 2 is 1. Negative 3 plus 1 is negative 2. And then we have a 0 here. Okay. So this was just minus R1 plus R3 and minus R1, or actually plus R1 plus R3 and minus R1 plus R4. And okay, so we've taken care of the first first column, we go to the second column, we want the one, this one is already here, so we want this and this and this to be 0. And so we'll multiply this row by -1 and add it to the first row. And when we do that, we get 1, 0, 4, 0. So have 0, 1, -1, 0. And then what we want to do, we want to get rid of this 2, so we'll have -2 R2 plus R3, and that gives us 0, 0. -2 times -1 is 2, so this becomes a plus 6. And then we want to get rid of this 1, so we'll have -R2 plus R4. That'll be 0, 0. And then this is going to be +1. This is going to be, did I do this? Okay. Yeah, this should be negative. Multiply this by +2 plus 2. That's 0. Is that right? Yeah. Okay. Sorry, because it's different in my notes, and yeah, I guess this is 0. Okay. All right. In any case, we can see what we're kind of where this is going. This is going to be this 0, 0, 6. We can just divide by 6, and we get 0, or what's it? 1, 0, 4, 0. 0, 1, -1, 0, 0, 0, 1, 0, and 0, 0, 0, 0. And right here, I think you can see that this once you get everything's 0 except this 1, we can see that we don't even have to really do the calculations or write down the row operations. We'll just multiply this row by 1, add to this row, multiply this row by -4. And what this will come out to be is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 0. Okay. And this shows you that this is the only solution is going to be when x equals 0, y equals 0, and z equals 0. Right? Okay. So there's no non-trivial linear combination of these. So the answer is yes. All right. Okay, and you might have been able to do this a little differently. You could see if there was any linear combination that whatever number is here and whatever number is here has to be opposite, because then we have a 1 and a -1 here and a 0 here. But in general, this process will always work. So if you let's try this one. Number 7, are these linearly independent? Okay, well, do the same thing. Again, we want an x, y, z, so x times this vector plus y times this vector plus z times this vector is 0. And we'll see that, okay, let's once again set up the augmented matrix. Okay. And I'm going to leave it to you to do the, well, let's quickly do it together. We have a 1 here. Let's eliminate the 3 and the 5. So multiply this by -3, add it to this, and we get 0, 1, -3, 0. And we multiply this by -5 and add it to this row, and we will get 0, 6, and then -5, that's -25 plus 7, that's -18. Okay. And once we get here, we can see that one row is a multiple of the other, so we can basically eliminate this row. Whenever you see one row is a multiple of each other, you can replace one of them with all zeros. Okay, and then we can add this row to this row, the second row to the first row, and we'll get 1, 0, 2, 0, and then 0, 1, 3, 0, and then 0, 0, 0, 0. Okay. Make this a, oops, sign error. Okay. Okay, so we get this now, and now we know how to solve this. It looks like there's going to be a solution because we have a row of zeros here. This says that 1x plus 0y plus 2z equals 0. This one says that 1y minus 3z is equal to 0. So we get that x can be written as minus 2z, y can be written as 3z, and z is just z. So that z is our free variable. Remember from last time, the columns with no pivots that correspond to the free variables. And that says we can let z be anything, so I'll let z be 1. If we let z be 1, that means x will be -2 and y will be +3. And sure enough, we get -2 times this first vector plus 1 times the second vector plus oops, sorry. I am so sorry. This should be a 3, and this should be a 1. And this is 5, 12, 7 equals 0, 0. Okay. That's 3. All right. And then since we have a non-trivial linear combination, these are linearly dependent. So the answer is no. These are linearly dependent. And in fact, the span of these is actually, the span of these vectors is going to be another plane. Say it won't be all of R3. Right? In general, if you have n linearly independent vectors, they're all automatically a spanning set for Rn. Okay. So we'll talk more about this next time. Again, get lots of practice, and see you next time.